So in this video we are going to discuss vector decomposition. Now if you're in my dynamics class, I know you've seen this before, at least to some extent. You know how to decompose a vector into, say, horizontal and vertical components. In other words, if this is the I-hat direction, and there's the j-hat direction vertically, I can take this vector, why don't I give it the vector name f, and I can write it in terms of horizontal and vertical components. Like so. So this fx would be the horizontal component, or the I-hat component of the vector, and fy would be the vertical component. Now remember, I is a unit vector, so when I say fx times I, what do I mean by that? What I mean is that fxi here is a distance, maybe not a distance, but an amount, I'll call it fx, in the horizontal direction, right? I unit vector fxi is this vector right here, which is an amount over in the I, in this case positive I-hat direction. Similarly, j is a unit vector, so fyj is an amount in the vertical direction, right? fyj. So f itself is the sum of these two vectors, fx in the I and fy in the j. Now again, this is a concept you should be familiar with. I'm hoping you are. Now in this video, I'd like to talk about vector decomposition a little more generally. Let's say I have this same vector f, and instead of decomposing it into horizontal and vertical components, let's suppose I want to decompose it into components along these two directions. Right? Again, these will be unit vectors that indicate directions. I'm going to call this one E hat red, or in short E hat R. I'll call this other one E hat blue, or E hat B there. Now you may have done this a little bit in statics, but we're going to do it in dynamics a lot, a whole lot. We're going to have to choose basis vectors that respect certain geometry or symmetry of a problem. We might choose different ways of drawing grid lines in space. So vector decomposition is going to be something that has to be almost natural to us. But in principle, it's the same thing we saw in statics. So what I'm going to want to do is I want to take this vector f and I'm going to decompose it into pieces. I'll call it fr in the E hat R direction plus an fb in the E hat blue direction. And let me move this down here so I can show you what this thing looks like. So let's think about what this is vectorially, right? fr E hat R. What is that? fr is a scalar multiplied by E hat R unit vector. So that's going to be a vector that's parallel to the E hat R direction. Right? FB E hat B, again, FB is a scalar. It's the component in the E hat B direction. That's going to be parallel to the blue direction. Right? And I'm going to take the red vector, take FR E hat R, add it to FB E hat B. Those are two vectors. I arrange them tail to tip. They should equal the F. So what does that look like? Picture it in your mind's eye. What does that look like before I show you what that looks like? Can you see that on here? Could you draw it yourself? Now, if you're still thinking about it, I want you to pause the video right now because I'm just about ready to reveal it. So here it is. So there's those two vectors. This one right here is the FR E hat R. Yes, it's a vector parallel to the E hat R direction. And I'm going to add to that F blue E hat blue. And F blue E hat blue is tangent to the E hat blue direction, or parallel to the E hat blue direction. And I've drawn these in a way so that when I arrange them tail to tip or tip to tail, this vector sum FR E hat R plus FB E hat B combine together to make this the original vector F, right? This is how I have to draw these things to get that vector sum to work out. Now I call this thing right here, I call that the vector triangle, right? The hypotenuse of the triangle is my original vector F, and these two other sides right here, those are the component vectors, right? Notice in this vector triangle, this angle right there, that's a right angle because these two basis vectors are perpendicular to each other, right? The E hat R and the E hat B, they're perpendicular to each other. Therefore, the component vectors, which are tangent to those basis vectors, they also have to be perpendicular to each other. So so this vector triangle is a right triangle by necessity, assuming that is I pick perpendicular basis vectors, which I'm always going to do. Now let me make another connection to what we saw previously with horizontal and vertical decomposition. I take these scalars, FR and FB, those things are my components. They are the components of my original vector F in the E hat R and the E hat B directions respectively. Right? FR and FB, again, they're just scalars, right? FR, FB, this is the component in the E hat R direction, right? FR is just this length right there. I shouldn't say length, this amount of the vector in the E hat R direction. FB is the amount of the vector F in the E hat B direction. And I want to observe something really important here. These FR and FB, they're scalars, but they're not just lengths, right? They have signs. Let me ask you a question real quick. What's the sign? FR is a scalar, it's just a number. What is the sign of FR? Is it positive or negative? And similarly for FB, is that a positive or negative scalar? So I want you to think about these signs. Pause the video. Tell me whether FR is positive or negative and FB is positive or negative. And then resume the video when you're ready. Okay, sign of FR. The answer is FR is positive. E hat R goes upward and to the right. This component of F has to be upward and to the right if the vector sum is going to work out. So therefore FR, this component vector, has to be in the same direction as E hat R. So FR has to be positive. That's the only way I can get that component vector to go into this direction right there. Yes? FB is the opposite. FB is going to be negative, right? Because in order to get these two vectors to add up to F, I need this component vector in the E hat B direction, I need to be in the opposite direction of E hat B itself. So the only way I can get FB, E hat B to go back down and to the right is if FB is negative. So that's what I get for that one. Yeah, does that make sense? Think about that one a bit. We know just from this construction of these two vectors that the signs or the components of FR have to be positive and FB has to be negative. So now let me ask you a question. When we did this formulation, when we draw in these vectors and expanding into components, notice that I constructed my vector triangle in this way. I first did the E hat R, FR E hat R, and then added to that the FB E hat B, right? I ordered my sum this way. Now vector addition is commutative, so I should be able to take these two vectors, swap them around, right? Take the blue vector first and add it to the red vector, and I should still get the same F, right? If I take the two vectors and swap them, right? So think about it. What would happen? Would that change any of the arguments I made if I do that? Well, check it out. If I add blue first and then add red to the blue and try to add them in a way that gets to this vector F again, then it's going to have to look like this, right? It's going to have to look like this. So the blue first and then the red. And if I do the construction this way, instead of the original way that I did, look what happens. The red component, the FR E hat R, it's exactly the same as it was before, right? It has the exact same length. It has the exact same direction. This FR is still going to be positive, right? It's exactly the same as it was before. The blue vector, here's the new blue vector. If I add blue first and then the red, this has the exact same length and direction as my original one, right? So it doesn't matter whether I add red to blue or blue to red. The vector triangle looks a little bit different, but the result is the same. I got the same resultant, I got the same components, and the vector decomposition naturally works if I do that. Now before we wrap up this video, let me show you a cute little graphic. Here's that vector that I called F before, and here it is split into E hat R and E hat B components. Now if I pick this up, I can see how other vectors would also be split into E hat B and E hat R components. Isn't that interesting to watch? So something like this would have both positive components. Something like this would both have negative components. And it's just sort of neat to see how, at least Of course, this is a subjective opinion. I think it's rather beautiful to watch this thing just sort of move around and how these vectors add up to the resultant vector, that black one. Yeah? So that's that for some vector f. We can also move the basis vectors around, so we can see how different basis vectors would decompose into some vector f, right? So, I don't know, kind of interesting to watch. Anyway, so that's all I have. There's vector decomposition.